So just before I just spotted a bug in my original code, so I just fixed it, and I'm going to explain this part of the code again. So as before, maybe we need to insert more finals because of the load result, we may need to insert finals, and those finals may in turn requires additional finals because the value to be inserted for the final should maybe the another final value. So in order to see whether this is the case or not, we are going to traverse the finals from here. So basically we are looking at each final that should be inserted, and we are going to find the values for the that are inserted at the final depending on the control flow graphs. So here we are going to look at the all previous, all the predecessors of the block for the phi node. And for each predecessor, we are going to do a very similar thing we did for the load results. We are basically looking for the AND value for the previous block, but if it doesn't exist, it may be possible that we need to look for the nearest block from the predecessor. So here is the thing. So here is the nearest block from the predecessor. So I'm going to explain the precise meaning of this nearest block when I'm going to visit the join tables. And yeah, after that we are going to look for the predecessor. The nearest block from the predecessor. We are going to get the value here, and we are going to use it. So if again it doesn't exist, we need to insert a phi node file for the predecessor's nearest join block. So if it is the case, we are going to insert it to the stack and try again from the continue the traversal. So this is basically a DFS search, and we are going to recursively look for which phi node should be inserted for this allocation ID. So this code is exactly the same with the code for the load instruction here. Yeah, some variables the variable names may be slightly different, but the essence is the same. And we are going to recurse into the traversal at this point of time. Okay, so far so good. And this var is signifying the value at the end of the execution at block this BID proof, which is the predecessor block, and we are going to insert this value as the value for the phi node when the control flows from this predecessor. So if the control flows from this predecessor block, then the phi node should be this value. That is meaning that. And we are collecting all this information into this, and so far so good. And this is so in overall, in summary, we are going to recurse this control flow graph and deduce which phi node should be inserted recursively. And after that, we are actually inserting phi nodes. So this is quite straightforward code. So I'm going to expect that you can see what's going on there from the code. We're actually inserting phi nodes. We are actually inserting the argument, and we are actually inserting here we are actually inserting a phi node variable here. So far so good. And at the end of the day, we are going to clean up the things. So first thing to do is that we are going to replace all the load results with the value calculated so far. So it is actually doing so. We are walking the tree we are walking the code for a function, and for each operand, we are going to see if it is the register that is to be replaced, and if it is the case, then we are going to actually replace it. So that is basically doing that. And after doing so, we are going to scan the code again, and we're going to change the store and load instructions for the promotable locations into a knob, because it does nothing. Store is going to be knob and load is going to be knob, which means that the location no longer holds valid information. It is just a bogus location, because the location is becoming a register right now. So far so good. So we're done here. So this is basically the algorithm of this memory optimization for KAIST, but we have a few missing details. The first thing to do is what's going on in the join table. So we looked for the nearest join block from a block for the load instruction and for each fine node. And here is the trick. So we are going to actually find if you're given an allocation ID and block ID, you are going to look for the nearest join block, which is basically doing so. So given a BID, we are seeing if it is contained in the joins, which is basically the set of the potential fine nodes. So if this joins contains AID, BID, which means that this block BID may potentially be inserted with a fine node for the allocation AID. So if it is the case, it's good. So we are going to return BID because it already is potentially inserting a fine node. Otherwise, we are going to look for the immediate dominator by looking at the DOM tree's parent. So we are going to replace BID with BID's immediate dominator and try again. So if it is a join point, we return. Otherwise, we look for a parent of the DOM tree. In other words, we are looking for the immediate dominator of the BID, and on and on and on until we get a join point, and we return it. So this is basically a small, trickery data structure that is remembering some results. So this is memorizing the internal results of the operation to reduce the time complexity. But the actual details doesn't matter at much for the purpose of this course. So if you just want to implement a correct memcache optimization, one you need to consider is just these a few lines of code. So we basically the thing is you are recursively recursively finding the immediate dominator until you get the join point. So when you get the join point, you just return the join point. So that's the semantics of this data structure, and all this code is only for the memorizing or memoization of the function results. Okay, so far so good. And at the next video, we are going to discuss how to construct the DOM tree. So here, in my code, it is implemented in this opt underbar utils.rs, and here we are going to construct a domination tree. It is not very long. It is just it is just a simple recursion, and I'm going to explain the code in the next video.